Dear students, in the last class we have discussed the differences between conductor, semiconductor, insulator, difference between intrinsic semiconductor and extrinsic semiconductor, and difference between p-type semiconductor and n-type semiconductor. So, very quickly we will revise the difference between the p-type semiconductor and n-type semiconductor. N-type semiconductor is obtained when a pure semiconductor is doped with pentavalent impurities, whereas p-type semiconductor is obtained by doping a pure semiconductor with trivalent impurities. The number of free electrons is greater than the number of holes. In p-type, the number of holes are greater than the number of electrons. Conductivity is mainly due to electrons. In a p-type semiconductor, the conductivity is mainly due to the holes. The majority charge carriers are in the conduction band, whereas in p-type, the majority charge carriers are in the valence band. The donor impurity level is closer to the conduction band, whereas in a p-type semiconductor, the accepted impurity level is closer to the valence band. So, these are the difference between the p-type and n-type semiconductor. So, now let me consider a single semiconductor crystal in which one end is doped with trivalent impurities, the other end is doped with pentavalent impurities. So, when one end is doped with the trivalent impurities, this part of the semiconductor becomes a p-type semiconductor, and the other end, which is doped with the pentavalent impurity, becomes n-type semiconductor. And this is the region that separates the p and n, and this type of arrangement is called a p-n junction. A p-n junction is one in which one end of the semiconductor is p-type and the other is n-type. In p-type semiconductor, the holes are the majority charge carriers and electrons are the minority charge carriers, whereas in the case of n side here, or n region, the electrons are the majority charge carriers and the holes are minority charge carriers. And now there is a difference in the concentration of the charges. Here the holes are more in number and here the electrons are more in number, and due to which the holes, they move from p-type to the n-type and the electrons, they move from n to the p region, and this type of movement of the electron is called as diffusion. So, therefore, this is called hole diffusion. So, from p side the holes move to the n region and electrons from the n region moves to the p region. So, that is called as electron diffusion. This process is called as the diffusion, and the diffusion is mainly due to the difference in the concentration or charge density, and this will result in a current, because any movement of the charges will result in a current. So, we get two currents here. One is the hole current as well as the electron current as well, and the net current is the sum of the individual current, and this is called as the diffusion current. And once the electron and the hole, they move across the boundary here, and the electron hole combination near the region creates an area where, because of the electron, we find no charge carriers in this particular region, and due to which only ions are left in that region. So, this region is free from the charge carriers and it contains only the impurity ion, for example, in the case of pentavalent, or so here, for example, okay, when we add trivalent impurity, we get an acceptor impurity ion. So in the case of N region, whenever we dope with the pentavalent, it donates an electron and becomes an ion, it becomes an positive ion. So therefore, we get a region in which there are no charge carriers. The charge carriers you will find only in these regions. And this particular region is called as the depletion region. The width of the depletion region is about 10 to the power minus 6 meter, 1 micrometer. And near the depletion region, whenever the electron hole combination takes place, further liberation of the electron and the hole takes place near the depletion region. That happens during the combination of the electron and the holes near the depletion region. And during that time, the electrons, they tend to move from P region to the N region, whereas the holes, they tend to move from N region to the P region. And this is called as the drift. So therefore, whatever the arrow which I have indicated initially is because of the diffusion. And now the drift takes place in the exactly opposite direction. So this is the diffusion. And this is the drift. So the drift takes place exactly opposite to the diffusion. So here you can see the whole diffusion in this direction and the whole drift is exactly opposite. And that diffusion and the drift, they cancel each other as they are in the opposite direction. Diffusion will result in a diffusion current and the drift of the holes will result in a drift current. And in equilibrium, these currents, they cancel each other as they are in the opposite direction. That means under equilibrium condition, there is no net movement of the charges takes place. And this depletion region will create a potential difference which is called as the junction potential. It is also called as the barrier potential, which is about 0.3 volt for germanium and then 0.7 volt for silicon. So because this region, it acts like negative terminal of the battery and this acts like the positive terminal of the battery, and that creates a potential difference in the depletion region, and that potential is called as a junction potential. The aim of this junction potential is to stop the movement of the charges from the N region and to the P region. And this type of device where we have one end is a P and the other is a N is called as PN junction diode, which we represent so like this. So this is the positive terminal and this is the negative region, or positive end of the diode, and this is the negative end of the diode. So therefore, whenever there is a PN junction is formed, one end is P side, the other end is N, and they are separated by a very small region called as a depletion region. We find charge carrier only in the P region and N region, but not in the depletion region. In the depletion region, we get to see only the ions. In P side, we find negative ions, and in N side, we find the positive ions. And there are two types of movement of the charges takes place. The drift takes place because of the formation of the charge carrier near the depletion region, and the diffusion takes place initially. That's because of the difference in the charge density. And in equilibrium, the diffusion current and the drift current, they cancel each other so that there is no net movement of the charges. If I consider a PN junction diode, this is positive and this is negative, and if I connect this to a battery, so that P side, positive side of the positive end of the diode is connected to the positive terminal of the battery, and the negative is connected to the negative terminal of the battery, and this kind of connection is called as the forward bias. So in forward bias, positive terminal of the battery is connected to the P region and the negative terminal of the battery is connected to the N region. So this is the depletion region, and this is the P end of the diode, positive terminal, N end of the diode, negative terminal. And here we have the negative ions, and then we have positive ions. So there is a junction potential. Let's take example of the germanium, which is about 0.3 volt. So initially, when this battery is switched on, this junction potential always opposes these charges, so that there is no movement of the charges takes place. So this is current versus voltage. This is forward bias, and this is the forward bias voltage. As we increase the voltage, this potential, it opposes the applied potential. So the field due to the applied voltage is from positive to negative, whereas the field due to the junction potential is exactly opposite. So this field opposes the applied field, and this field opposes till the applied voltage reaches 0.3 volt. So that is the reason why initially there is no current in the circuit. Not only that, as we apply more and more voltage, this positively charged holes, they move towards the junction because they are repelled by this particular battery, whereas the electrons, they move in this direction because they are repelled again. So the majority charge carriers, which are the holes, and here the majority charge carriers, which are the electrons, they move towards the junction. And the result of this is that the width of this depletion region decreases. The width becomes lesser and lesser because more and more charge carriers, they move towards the junction. And after that, this depletion region, it vanishes beyond the voltage which is equal to 0.3 volt, which is the junction potential. And once it vanishes, the charges, they move, they cross very easily, and that will result in a current. The movement of the electron is from N to the P region, it's like this, and that will result in a current in an opposite direction, and this current is called as the forward bias current. And that's how the current rises in the circuit, and this is the kind of graph we all have drawn in the experiment forward bias characteristic curve. So where we have a voltage beyond which the current rises sharply. So this is called as a knee voltage, or it's called as the cut-in voltage. So this is how we mark. And since the current rises very sharply, this particular device, the diode, it offers very less resistance or low resistance. Therefore, in forward bias, there is a large current flows. By the way, that current, even though it's very large, it is of the order of a milliampere, and forward bias voltage is in volt. So the charge carriers, which are the majority charge carriers, they move towards the junction. That will result in decrease in the width of the depletion region, and large current flows, because of which this diode offers very low resistance, or it acts like a closed switch. Forward bias or a diode in the forward bias, it acts like a closed switch. So what is forward bias? When the positive terminal of the diode is connected to the positive terminal of the battery and negative terminal of the diode is connected to the negative terminal of the battery, then such bias is called as a forward bias. And if no voltage is applied, then the diode is said to be in the unbiased state. Diode is in the unbiased state. And in forward bias, till certain voltage, there is no flow of the current, because the applied field is opposed by the field due to the potential near the depletion region, which is called as the junction potential. So this is called forward bias characteristic curve, where we draw current versus voltage. In this particular circuit, if I reverse the polarity, that is, if the positive terminal of the battery is connected to the negative terminal of the battery, and negative terminal of the diode is connected to the positive terminal of the battery, then the diode is said to be in the reverse bias. So let us see what happens, or how exactly the diode behaves in reverse bias. So in reverse bias, so this is the diode, this is the P region, and this is the depletion region. Negative ions at the P side and positive ions at the N side. So P end of the diode is to be connected to the negative terminal of the battery, and N side is to be connected to the positive terminal of the battery. Only then the diode is said to be in the reverse bias. Now in P side, the majority charge carriers are the holes, and inside the negatively charged electrons are the majority charge carriers, and here the minority charge carriers are the electrons. Here the minority charge carriers are the holes. Now majority charge carriers, which are positive, are attracted by the negative terminal of the battery, and the majority charge carriers, electrons, are attracted by the positive terminal of the battery, and due to which these majority charge carriers, they tend to move away from the junction, and the result of that is this width of the depletion region. This width, it increases. In forward bias, the width of the depletion region decreases, but here the width increases. And since the majority charge carriers are moving away from the junction, the amount of the current in the circuit is almost negligible or zero. So we draw the current versus voltage in the third quadrant. Due to the majority charge carriers, there is no current because they move away from the junction. But look at the minority charge carriers, the electrons are repelled by this negatively terminal of the battery, negative terminal of the battery, and positive charges are repelled by the positive terminal of the battery, and due to which they move towards the junction. So in forward bias, the charges that are moving towards the junction are majority charge carriers, whereas here the charges which are moving toward the junction are minority charge carriers, and the current that results in the circuit, you can see the electrons, these electrons, they move towards like this, and that will result in a current which is called a reverse bias current. And the value of this reverse bias current is very less, because it is the current that results is because of the minority charge carriers. So that's why we get a very small current through the circuit. which is of the order of micro ampere. And this is the kind of current that we get. But later, once we go on applying the voltage, the junction breakdown takes place, and due to which current rises sharply for a particular voltage, and this is called as the breakdown voltage, and that takes place only beyond a certain voltage where the current increases for almost the constant voltage. So, for this part of the region, as the voltage increases, current remains almost constant, but beyond a certain voltage remains constant, but the current increases. So, this is the kind of the graph that we get in the case of reverse bias. And since the current is very less, of the order of microampere, the resistance offered by the diode in reverse bias is very high compared to that in forward bias. It is almost 1000 times, because the current in forward bias is of the order of milliampere, but in forward bias it is of the order of microampere. Current has reduced by a factor 1000, it has reduced. That means that even the resistance also should increase by a same factor, which is 1000 times more compared to that in forward bias. So, and again in reverse bias, since it does not allow the charges to flow, it acts like an open switch. So, that is the difference between the forward bias and the reverse bias. So, the conclusion from the forward and the reverse bias is that the diode conducts only when it is in the forward bias, and it does not conduct in the reverse bias. It conducts, but the conductivity is very, very less. So, therefore, it has a unidirectional property. So, let us see the differences between the forward bias and the reverse bias. So, when do we say that the diode is in the forward bias? When the positive terminal of the battery is connected to P region and negative terminal to the N region, then the PN junction is said to be in forward bias. So, what is the definition of the reverse bias? When the positive terminal of a battery is connected to N region and negative terminal to the P region, then the PN junction is said to be in reverse bias. The current is due to the majority charge carriers. This is in forward bias. In reverse bias, the current is due to minority charge carriers. And since it is due to the majority charge carriers, the order of the current is in milliampere, whereas in reverse bias, it is of the order of microampere. The other difference is the thickness of the depletion region decreases as the bias voltage increases. And in reverse bias, the thickness of the depletion region, it increases as the bias voltage increases. The diode offers very low resistance, whereas in reverse bias, the diode offers high resistance. The diode acts as an on switch because it conducts in the forward bias, whereas in reverse bias, the diode acts as off switch. So, resistor is a device which conducts equally in either direction, whereas the diode is one which has a unidirectional property. That means it conducts only when it is in the forward bias, and that particular property is used in one more application, and which is called as a rectifier. So, which I am going to explain in my next class. Thank you.